Hi everyone, this is a video for Class 8 of PH 125, and today we're going to be talking more about vectors. So we'll review a little bit the stuff that we covered in the last class, and we'll also talk a little bit more about vectors, and then we're going to go ahead and apply that knowledge to two-dimensional kinematics. So let's start with a quick review about how we add and subtract vectors. So we have our example here. We want to know C, and C is equal to A plus B, where A and B are vectors. And first of all, we learned this graphical method for finding the vector addition of A plus B to get C. And what we do there is we just take our vector A, we draw it out. So remember, our vector is drawn out in an arrow form where its length corresponds to the magnitude of the vector, and then the direction of the arrow corresponds to the direction of the vector. And then if we want to add A and B, what we do is we take our vector B and we place it so that the tail of B, so the end without the arrow, is placed at the tip of A, which is the end with the arrow. Okay, and then our vector addition, our C vector here, is going to be the arrow that stretches from the tail of A to the tip of B. So that's our graphical method for adding vectors, and that's wonderful, and I always do that even when I want to know firm numbers. I always make a sketch like this so that I have an idea of what the sum of A and B is going to be. However, if you actually want to get numbers out, so you actually want to know the magnitude of the vector C and its angle relative to some axis, then really what we're going to want to do is add using vector components. Okay, so here's our example here. How do we add and subtract using vector components? The first thing you want to do, remember, is define a coordinate system. So generally we'll choose the positive x direction to be pointing to the right and the positive y direction to be pointing up. That's our usual definition of our coordinate system. And then what we can do is we can take all of our vectors, so in this case we'll take A and B, and we'll break them up into vector components. So when I say vector components, I mean AX and AY for the vector A, and BX and BY for the vector B. So for example, if we look at this vector A, remember AX just tells us how much that vector stretches in the x direction. Similarly, AY tells us how much the vector A stretches in the y direction. And we can find AX, AY, BX, and BY using trigonometry, so you'll want to remember your SOHCAHTOA relationships there. All right, then once we have our vector components, what we want to do is we want to add like components to find the vector components for our summed vector C. So if you look at this diagram over here on the right-hand side, you can see that the total amount that the vector C, so that's this green arrow, the total amount that it stretches in the x direction is going to be the sum of the x component of vector A and the x component of vector B. So that sum gives us the total sum of the amount that the vector C stretches in the x direction, and so that's our x component of C, or in other words, Cx. Similarly, we can find Cy by adding AY and BY. All right, and so then once we do that addition, we end up with C written out in what I would call vector component notation here. So you'll have Cx multiplied by x hat. Remember, that's the unit vector with a magnitude of 1 that points in the x direction. And then we have Cy multiplied by y hat. That's the unit vector that points in the y direction. Okay, and that is the answer for C. That's a perfectly good way to represent C. That's the vector component notation for writing out C. But oftentimes you'll be asked to find the magnitude and direction of C. So if that's what you're asked for, then you're going to need to do one more step here. And we'll want to remember that Cx, Cy, and C, they form a right triangle here. So it's like this little right triangle right there. Is formed by Cx, Cy, and C. And then you can go ahead and think about the magnitude and direction of the vector C using trigonometry again. So we can find the magnitude of C, which is the length of the hypotenuse of this little right triangle, using the Pythagorean theorem, which tells us that C is equal to the square root of Cx squared plus Cy squared. And then we can find the angle theta that's inside this right triangle here. So that would be this little angle here. We can find that angle using the inverse tangent, for example, of Cy over Cx. Okay, and so just one quick comment on that angle theta. When you draw out your little right triangle that's formed by Cx, cy, and c, it might not be in this first coordinate. So it might not have a positive x component and a positive y component. And so you have to be a little bit careful about what that angle theta that you're finding using the inverse tangent, what is it defined relative to? So in this case, I would say that it's defined above the positive x-axis, and that's generally how you're going to want to define theta, especially when you're answering questions on your homework. Okay, and so that's vector addition. How do we do vector subtraction? It's very similar. So the basic idea for vector subtraction is that you're really, if you want to do like a minus b equals c, for example, really you're just multiplying b by a -1. Okay, and so what happens when we multiply b by -1? We flip its direction. So if you look at b up at the top here, you can see that the arrow points kind of upwards and out to the right. And so if I want to multiply by -1 and get minus b, I just flip the arrow end. So in other words, the tail becomes the tip and the tip becomes the tail, right? So I've just flipped which end gets the arrow. That gives me minus b. And then once you do that, you follow the same steps as we had for vector addition. Okay, so let's go ahead and do a quick practice problem in working with addition and subtraction of vectors here. So you're given two vectors, A and B, on the right-hand side, and we want to know which of the choices A, B, or C given on the left-hand side, so the green arrows, corresponds to C equals A minus B. Okay, so to solve this problem, remember that the first thing we need to do is remember that when we take A minus B, we're really like adding A to minus B, right? And so what we want to do is we want to find minus B, and to do that, we just flip the arrow end on our vector B, right? So we flip the end that's the arrow and the end that's the tail. So now I have minus B, and then if we want to graphically add A to minus B, what we do is we just take the vector A and we place the tail of minus B at the tip of A, and then our vector C is going to connect the tail of A to the tip of minus B. Okay, and so I get this green arrow here, which looks a lot like answer choice A to me, and so I would go ahead and pick answer A. Okay, so that's adding and subtracting vectors, but what if we want to multiply a vector by a scalar? So remember, a scalar is just a number with units perhaps, but it doesn't have a direction. All right, and so it turns out that this is something that we've already been doing quite a bit. For example, we did this when we were subtracting vectors. So let's look at an example here. So say we have some vector A, which I've drawn in on a coordinate system so that its tail is at the origin of that coordinate system. If we were to think about that vector, we could write it out in terms of its components, right? And so the x component AX would be how far that vector stretches in the x direction, so along that x-axis, and then the y component would be how much that vector stretches in the y direction. Okay. And so then when we were subtracting vectors, remember we would need, for example, if we were trying to subtract A from something, we would need minus A. And we said that minus A was just, we take this vector A and we switch the ends that are the tail and the tip, right? So if I were to do that and then place minus A so that it's still on this coordinate system with its tail at the origin, then I would get something that looks like this red vector here. So now let's think about the vector components of minus A. So what's the x component of minus A? Well, again, it's just how much this vector stretches along the x-axis. And you can see that it stretches the same amount along the x-axis as our vector A did, but now instead of stretching to the right, it's stretching to the left. So I would say that the x component of minus A is going to be minus AX. Similarly, if we were to think about the y component of minus A, it's the same length, right? So it stretches in the y direction the same amount as our vector A did, but now instead of going up, it's going down. And so I would say that the y component is going to be minus AY. And so what did we do when we multiplied A by minus 1? Well, really, we just distributed that minus 1 to the components of A. Okay, so mathematically we could write it out like I have shown up here above. When we take minus A, we're really multiplying by the scalar minus 1. And then we just distribute that scalar to the components of the vector A. All right, and so this is true for any scalar. We did it for minus 1 here, but we could do it for any scalar. So let's say that we have some scalar C. Then if we define some vector B to be equal to the scalar C multiplied by the vector A, all we have to do is distribute that scalar C to the components of the vector A to get our vector B. So for example, the x component of B would be C times AX, and the y component of B is just going to be C multiplied by AY. All right, and it turns out this is actually what we've been doing for our unit vectors x hat and y hat all along. So this was how we were able to get any vector that we want by multiplying those unit vectors by some scalar. So this is something that we've really already been doing quite a bit. All right, so now let's talk a little bit more about what happens to this vector b when we multiply a by that scalar. So what is going to happen to the magnitude of the vector? Well, it turns out that the magnitude of the vector b is just equal to the magnitude of our scalar multiplied by the magnitude of the vector a. So that's maybe fairly intuitive. All right, and then when we think about the direction of the vector, it turns out the direction of the vector doesn't change unless we're multiplying by a negative scalar number, in which case the direction of the vector flips, just like we had in our example up above. So let's take a closer look at those two things. Okay. So here, when we think about the magnitude of our new vector b, we can actually explicitly calculate it out using our Pythagorean theorem. So remember, the magnitude of b is going to be equal to bx squared plus by squared, and then you take the square root. Bx, remember, is c times ax, and then by is going to be c times ay. So we can just plug those into our Pythagorean theorem. Then we see that we're going to end up distributing that squared to each of those terms, right? And so we'll end up with a c squared in both terms in the sum, and so we can pull it outside of our sum. Okay, so we end up with the square root of c squared multiplied by ay squared plus ax squared. All right, ay squared plus ax squared, well, that's just a squared. So that's the magnitude of our vector a squared. All right, so we end up with the square root of c squared multiplied by a squared, which in other words is just the magnitude of c multiplied by the magnitude of our vector a. And so here you can see that the length of the arrow that represents our vector is just going to be exactly scaled by that scalar that we're multiplying by. Okay, how about the direction? So when we think about the direction of a vector, we're going to think about some angle theta, generally defined above the positive x-axis. And so when we think about how we can calculate that direction, we usually use inverse tangent of the y component of our vector divided by the x component of our vector. And so here that's going to be c multiplied by ay, that's equal to by, divided by c multiplied by ax, or in other words, bx. Okay, then you can see that we have c's in both the numerator and the denominator here, and so those will cancel out. And so it's going to be equal to the inverse tangent of ay over ax. Well, that's exactly equal to the angle that defines our vector a. And so here you can see that the angle that defines vector b is going to be equal to the angle that defines vector a, unless, of course, we have this negative scalar that's multiplying through. Because we have this strange thing with the harmonics of the tangent, cosine and sine functions, you end up getting the same angle, but actually it corresponds to an angle that has been flipped by 180 degrees. So in other words, the angle of our vector b is going to be equal to the angle of our vector a plus 180 degrees. So let's look at some examples here. So I have some vector a, which has components ax and ay, and it forms an angle theta here. I've drawn it above the negative x-axis, right? So this axis here would be like pointing in the negative x direction. So I would say that that's the angle above the negative x-axis as drawn in here. Okay, and so then when I think about some new vector, which is 1.5, which is just a scalar, multiplied by my vector a, I would end up with a length arrow that's 1.5 times my original a vector arrow, right? So the length of that arrow just scales exactly with the multiplied scalar, so 1.5 times in this case. And then you can see that you also would multiply each of the components, so each of those components would grow by 1.5 times, but the angle in this case is going to stay the same as for our original vector a, just like we would expect. Now let's look at a case where we have a negative scalar being multiplied here. So we have minus 0.5 multiplied by our vector a. As you expect, that new vector 0.5a is going to be half the length of our original vector a. So that's just what we expect. Because we're multiplying by this negative sign, we're going to flip the arrow and tail ends, right? So we flipped those. In other words, the new angle theta is going to be equal to our old angle theta plus 180 degrees. All right. Let's do another example here. So we have vectors A and B drawn out again on the right-hand side, and we want to know which of the green arrows on the left corresponds to some vector C, which is equal to 2 times the vector B. Okay, so remember when we multiply by a scalar, here we're multiplying by the scalar 2. What ends up happening is we keep the same direction, but we're going to change the length of our arrow by exactly that factor of 2. And so here I would draw a vector 2b in that's double the length, but in the same direction as b. And so then looking at my options, I would say that that corresponds to answer C here. Okay, so that kind of wraps up our summary of vectors. I know this chapter has been a lot of math, and now we're going to go ahead and apply that math and get back to the physics a little bit. So we're going to circle back to our kinematics terms: position, displacement, velocity, and acceleration. Remember from chapter 2. All right, so I'll just remind you, position is location relative to a defined coordinate system. Displacement is change in position. Velocity is the rate of change of position, so how fast that position is changing, and acceleration is the rate of change of velocity, or in other words, how quickly that velocity is changing. So that all comes from chapter 2. And in chapter 2, we were specifically focused on one-dimensional kinematics, and so we assumed that displacement, velocity, and acceleration were all happening in a single direction. So we called that direction, just in general, we called it the x direction, and so position, displacement, velocity, and acceleration were all in the x direction. Then, because these are vectors, we were able to assign the directions of the vectors just using plus or minus signs. And that was perfect because everything was happening along a straight line. All right, but now what if we allow our motion to expand into 2 dimensions? So it's no longer confined to a straight line. It can happen in any direction along a 2-dimensional coordinate system. And this is also true if we were to expand into 3 dimensions. Then our direction is going to be given in terms of vectors and vector components instead of just thinking about plus or minus signs. And so that's going to allow us to generalize these 4 different terms that we think about in terms of kinematics, so position, displacement, velocity, and acceleration, into 2 and 3 dimensions. So how are we going to do that? Well, we're going to keep the same general definitions as we had in 1 dimension, but now each of these 4 things, so position, displacement, velocity, and acceleration, will have components in the x and y directions. So they're going to be vectors that can be, in general, stretching in 2 dimensions. Okay, so I'm going to leave this chart here. You are definitely welcome to look at it for reference, but we're going to go through each of these terms in detail. All right, let's start with position. Specifically, we're thinking about position in 2 dimensions now. So in 1 dimension, we called position x. Now in 2 dimensions, we're going to use the more general vector, which is r. So our position is still just location relative to a defined coordinate system. It has dimensions of length, which means in SI units, we're going to be using meters whenever we're talking about position. Okay, so let's think about our coordinate system that I have drawn in here. Remember, position is location relative to a defined coordinate system. And so what that means is that the vector r is going to point from the origin of the coordinate system to some point on our coordinate system defined by x, y. So if I were to just pick any point on my coordinate system, and I'll say that that point has coordinates x, y, then my vector r is just going to point from the origin right to that point. Okay, so now we want to think about the vector components of r. So if I were to think about the x component of r, remember that's how much r stretches in the x direction. So here, if we were to just sketch that in, I would get this blue dashed line that I have here, and we can see that the length of that blue dashed line, that's just going to be x, because remember this vector r points to the coordinate x, y. Okay, so that's going to be the x component of my vector. Similarly, if we were to think about the y component of the position vector, that's just the length that this vector stretches in the y direction, which is defined by y. Okay, and so then I can think about my position vector in terms of x and y components, and I can write it out as r equals x multiplied by x hat plus y multiplied by y hat, where x is the x component of the position r and y is the y component of the position r. We could use rx and ry, but that notation gets a little clunky. It's easier to just use x and y. Okay, so then if we were to think about the magnitude of the position vector r, we would just look at this little right triangle that we have here, and we know that we can use the Pythagorean theorem. So then r, which is the hypotenuse, is just equal to the square root of x squared plus y squared. We can also think about the direction of the vector r, so the direction of the position vector, and that's going to again be given by our trig functions. Here we could use theta is equal to the inverse tangent of y over x, where again this theta we would have to be careful about how we're defining this direction. Specifically here it's defined above the positive x-axis for that triangle that's drawn in. Okay, so next up let's talk about displacement in 2 dimensions. So remember when we were talking about displacement in 1 dimension, we called it delta x because the change in position was always happening in the x direction. Now we're allowing our general change in position to happen in any direction, so we're going to call displacement delta r. Okay, it has dimensions of length, and so it's going to have SI units of meters, just like position. And now if we were to think about what does delta r, this displacement, really represent, it's going to be the vector that points from the initial position to the final position. Again, this is exactly like what we did in 1 dimension. All right, the initial position vector, we call it r initial. It's just going to have a component in the x direction of x initial and a component in the y direction of y initial. So in other words, it's the vector that points to some initial position defined by the coordinates x sub I, comma y sub I. All right, then if we were to think about final position, we call it r final, and it's going to point to the point on our coordinate system that's defined by x final, comma y final. All right, so those are my initial and final position vectors, and then we know the displacement is going to be the vector that points from the initial position to the final position. So if we were to sketch that in here, we would get this purple vector, which I call delta r. So it points from my initial position to my final position. Okay. Then if we look at this figure, we can see that we actually have like vector addition happening here. So if you start at the origin, if you go along r initial, then you can see that delta r is placed so that its tail is at the tip of r initial. And then you can see that r final points from the tail of r initial up to the tip of delta r. So graphically then we could see that r initial plus delta r is going to be equal to r final. That looks just like our vector addition types of problems. And that makes sense because that tells us that our final position is equal to the initial position plus the displacement, and the displacement just tells you how far you moved, right? So logically, that equation makes sense. And so then we can go ahead and rearrange that equation to get an equation for the displacement in terms of r final and r initial. If we rearrange, we get delta r, so our displacement is equal to the final position minus the initial position, just like we would expect, because remember this delta always tells us that it's final minus initial. Okay, we can write out delta r in terms of components. Remember, when we add and subtract vectors, we are only adding and subtracting like components. So really, when we take r final and we subtract r initial from it, what we're going to end up doing is we're going to subtract x final and x initial. That's going to get multiplied by x hat, right? So that's going to give us the x component of our displacement. Similarly, the y component of the displacement is going to be given by y final minus y initial. Remember, the x hat and y hat components don't mix together. Okay, graphically we can look at this over here. So I have my same little figure drawn out with delta r drawn in. What do those x and y components of delta r represent? So if we were to look at those, you can see that the delta r vector, it stretches an amount in the x direction that's given by x final minus x initial. So that's going to be this little purple dashed line in here. X final minus x initial, that's exactly delta x. That's the displacement in the x direction that we defined when we were talking about one-dimensional kinematics. All right, similarly, we can think about how far this vector stretches in the y direction. You can see here that that amount that the vector stretches in the y direction is exactly equal to y final minus y initial, and we can call that delta y, or in other words, that's like the displacement in the y direction. So a simplified way to write out our displacement in 2 dimensions is delta r is equal to delta x, the displacement in the x direction, multiplied by x hat, plus delta y, or in other words, the displacement in the y direction, multiplied by y hat. Okay, so we should be starting to see a pattern here. We're going to end up writing out our vectors in terms of an x component multiplied by x hat and a y component multiplied by y hat, where those components are defined exactly like we did when we were talking about one-dimensional kinematics in chapter 1. Okay, let's do a practice problem here. So we have a clock, and its minute hand originally points at 12, and then it's moving to point at the 3 after 15 minutes. And if the hand is 5 centimeters long, we want to know what is the displacement of the tip of that hand as that clock hand moves from the 12 to the 3. Okay, so how would I solve this problem? Well, I would think about the clock hand that we have drawn in here. I would think about that clock hand, the arrow, as representing the position vectors at our initial and final times of the tip of the clock hand. So in other words, if we were to define the origin of our coordinate system here as the center of the clock, and we use our usual convention that plus y is up and plus x is to the right, then we can go ahead and think about our initial position vector, which we would call r initial. It points to a location on this coordinate system that's going to be at x equals 0, right? Because it's all along the y-axis here. It's straight up. And then at 5 centimeters in the y direction, because we know the length of the clock hand is 5 centimeters. Okay, so my initial position is going to be at 0 centimeters in the x hat direction and 5 centimeters in the y hat direction. All right, how about our final position of the tip of that clock hand? Well, it points to the point that's all along the x-axis, right? So it's going to be 5 centimeters along the x-axis and 0 centimeters along the y-axis. So in other words, x final is 5 centimeters and y final is 0. Okay, so from there, finding the displacement is fairly straightforward. Remember, we want to subtract like components. So we want to subtract x final and x initial to find the x component of the displacement, y final and y initial to find the y component of the displacement. Okay, so then we just have to plug in our numbers. We know x final is 5 centimeters, x initial was 0, and then we know that y final is going to be 0 while y initial was 5. So when we plug those in, we should end up getting our answer C here, which is that the overall displacement is a displacement of 5 centimeters in the x hat direction and minus 5 centimeters in the y hat direction. Okay, now let's talk about velocity in 2 dimensions. Remember, velocity is rate of change in position. Velocity has units, SI units of meters per second, or in other words, it has dimensions of length per time. Okay, so now we're going to think about our definition for average velocity. Just like we did in 1 dimension, it's going to be displacement divided by time. Now our displacement is the general displacement delta r. We're dividing by the elapsed time, which we call delta t. Okay, and so if you look at this equation here, we have a vector that's essentially going to be multiplied by this scalar 1 over delta t, right? So we can define our scalar 1 over delta t. Time doesn't have direction, it's always positive. And so what that means is when we multiply our vector, the displacement delta r, by that scalar, our resulting vector is going to point in the same direction as the displacement, as we learned a little bit earlier in this lecture. So what does that mean for us? It tells us that the average velocity over some amount of time is always going to point in the same direction as the displacement during that same amount of time. So graphically, we can think about this by drawing a graph that plots the position as a function of time. So in other words, each point on this blue curve represents the position, where position is the 2-dimensional position at a particular moment in time. So for example, I've picked out 2 points on this plot. I've picked out my initial position and my final position. Initial position is defined by x initial, y initial, and the final is defined by x final, y final. Now we know displacement is going to point from the initial position to the final position. So we could draw in our displacement vector here, delta r, and it's just going to point from that initial position to the final. Then, because we know that our average velocity has to be in the same direction as that displacement, we can immediately see that the average velocity between those 2 time points is going to be parallel to that delta r vector. So we can intuit what direction the average velocity is going to be between those 2 times. Okay, now we can think about our average velocity in terms of x and y components as well. So to do this, we remember that the displacement is really like the displacement in the x direction, so delta x multiplied by x hat plus delta y multiplied by y hat. And then remember, when we take our multiplication by a scalar, 1 over delta t, that's really going to be the same thing as distributing the 1 over delta t to each of the components of our vector delta r. So we can distribute 1 over t to each of those components, and then we see that we get v average is equal to delta x over delta t x hat plus delta y over delta t y hat. And hopefully we recognize delta x over delta t from our one-dimensional kinematics chapter. That was just what we called our average velocity in the x direction when we were talking only about one-dimensional kinematics. And so we can call that Vx average here, so it's our average velocity in the x direction. And then similarly, we can call delta y over delta t Vy average. And so we see that V average is just going to be equal to Vx average x hat plus Vy average y hat. So in other words, it's just going to be an average velocity in the x direction plus an average velocity in the y direction. Okay. Now we can also think about instantaneous velocity. So just like we did in one dimension, we define our average velocity, which can occur over any period of time. And then we think about instantaneous velocity, which is occurring at a given moment in time. So it's the same definition, it's displacement per time, but we just take the limit that that time is going to a very short period of time. So just one instant in time. All right, and then we'll often drop the instantaneous when we talk about instantaneous velocity, and we just call it velocity. So if ever you see velocity, that means instantaneous velocity. Okay, and so the instantaneous velocity is going to point in the same direction as the instantaneous displacement, or in other words, the direction of motion at a given moment in time, because again, we're just multiplying this vector by our scalar delta t, 1 over delta t. So graphically, what does that mean? If we were to think about the displacement at a given moment in time, that would be in the direction that's tangent to the curve at that particular moment in time. And so then we could say that the instantaneous velocity at a particular moment in time, so when your position is x and y, it's just going to be in the same direction as the tangent to the curve at that location. Okay, and so then when we think about the magnitude of this instantaneous velocity, that's what we call the speed. And for speed, we just use v in italics, so no bold and no vector symbol. It's the same thing as taking the magnitude, right? So if you take the absolute value of the vector v. Okay, and so then we can think about our instantaneous velocity in terms of x and y components, just like with our average velocity. So we could think about an instantaneous component of our velocity in the x direction multiplied by x hat plus an instantaneous velocity in the y direction multiplied by y hat to get our overall instantaneous velocity vector. Then if we were to do that, then the speed, or remember the magnitude of the instantaneous velocity, is just the square root of the x component squared plus the y component squared. All right, let's do a quick example with velocity here. So again, we're thinking about our clock, and we want to think about the tip of the hand of that clock. And we want to know what is the average velocity of that tip if it takes 15 minutes for that, that tip of the hand of the clock to move from the 12 position to the 3 position. And remember that the clock hand is 5 centimeters long. Okay, so remember from our last example, we already know the displacement of the clock hand during the amount of time that the hand is moving from the 12 over to the 3, right? So we already know that the displacement over that time frame is 5 centimeters in the x hat direction and minus 5 centimeters in the y hat direction. Okay, and so then all we need to do to find the average velocity over that time frame is to divide by the amount of time that it takes for the hand to move. So here, to go from the initial position at the 12 to the final position at the 3, remember it takes 15 minutes. We assume this is a well-working clock here, and so we want to divide by 15 minutes. We divide each of the components by 15 minutes, right? So we're distributing that 1 over 15 minutes to each component of our average velocity vector. And so if I were to do that, you would end up getting 0.3 centimeters per minute in the x hat direction and minus 0.3 centimeters per minute in the y hat direction, which corresponds to answer A here. Okay, so our last kinematic property that we want to talk about today is acceleration in 2 dimensions. Acceleration, remember, is rate of change in velocity. And acceleration has units of meters per second squared, or in other words, dimensions of length per time squared. All right, let's start by thinking about average acceleration. Remember, we defined our average acceleration to be the change in velocity per unit time. So in other words, it's change in velocity over some elapsed time, where that elapsed time can be any duration in time. All right, let's think about this change in velocity that we have in our numerator here. Really, that's the change in the instantaneous velocity. So in other words, it's v final, the instantaneous velocity at your final time, minus v initial, which is your instantaneous velocity at your initial time. And you'll notice here both v final and v initial are vectors, and they can have components in the x and y directions. So for example, we could think about v final as being equal to v final x hat. So that's going to be the x component of v final plus v final y hat, where v final y, vfy, is the y component of your instantaneous final velocity. And we could do something similar there for v initial. All right, and so then we could write this out in terms of vector components. We could think about a change in velocity in the x direction. So in other words, that's going to be like our vx final minus vx initial. Because remember, when you subtract vectors, you only subtract like components. So we could think about a change in velocity in the x direction divided by delta t to give us our average acceleration in the x direction over that amount of time, delta t. And then we can add that to our change in velocity in the y direction, which would be vy final minus vy initial divided by delta t. Again, that comes from the fact that we can't mix our x and y components when we do this vector subtraction of v final minus v initial. All right, and so then delta vy divided by delta t is going to give us our average acceleration in the y direction, which we call ay average. Okay, and so then the overall acceleration is just going to be the x component of the average acceleration multiplied by x at plus the y component of the acceleration multiplied by y hat. Okay, then we can also think about instantaneous acceleration, which is really just the acceleration at a given moment in time. We define this by just making sure that the amount of time delta t that's in our denominator here, we let it be vanishingly small, so that delta t is like 1 moment in time. All right, and then just like how we call instantaneous velocity, we refer to that as just velocity. Similarly, whenever you see acceleration, it's referring to the instantaneous acceleration. Okay, we can write out our instantaneous acceleration in terms of components as well. So we can think about an x component and a y component, which would just correspond to the instantaneous change in the velocity in the x direction and the instantaneous change in the velocity in the y direction, respectively. All right, then if we were to think about the magnitude of the acceleration, we're just going to think about using our vector components. And so we know that the magnitude of the acceleration is going to be ax squared plus ay squared, and then we take the square root to find that magnitude of a. All right, last thing to note here is that acceleration is going to be in the same direction as the change in velocity, which really just comes from the fact that when you think about our definition up top, delta v over delta t, remember delta t is a scalar. It's always positive. 1 over delta t is also a scalar, and it's always positive. So really we're multiplying our vector delta v by our scalar 1 over delta t. And when we multiply by a scalar, we don't change the direction. Okay, and so that means that our acceleration is going to be parallel to the change in velocity. And in general, that's not going to be the same direction as the direction of motion. So let's just look at a quick example here. We'll go back to our position, which is plotted as a function of time. We learned in the last slide that the instantaneous velocity corresponds to the tangent to the curve at a particular moment in time. So for example, if we were to pick our initial position here, then we know that our initial velocity, the instantaneous velocity, would be the tangent to the curve at that particular location. And similarly, at our final location, our final position, we're going to get a final velocity that's tangent to the curve at that particular position. Okay, so we've picked out our final and initial velocities here. And then to find the average acceleration direction, we need to find the direction of the change in velocity. So to do that, we can remember that delta v is equal to v final minus v initial. So we take our v final vector, we place it here, and then remember to subtract vectors, we want to switch the direction of the tail and the tip of v initial. So we swap those, and then we place the tail of minus v at the tip of v final. And then delta v, which is v final minus v initial, is going to stretch from the tail of v final to the tip of v initial. Okay, and so then we have our delta v vector, and we know that the average acceleration is going to be parallel to that vector, which, as you can see, does not point in the direction of motion along that time frame between our initial and final positions. So it's not in general going to be in the same direction as the direction of motion. One last thing to note here, something that kind of strange that happens, an object can have a constant speed, but it can have non-zero acceleration if the direction of the velocity of that object is changing. So in other words, if that object is moving at constant speed, but it's changing direction, well, it must be accelerating to change that direction. And this is something that happens, for example, when we have uniform circular motion, which is something that we're going to study in detail a little bit later on. So just something to keep in the back of your mind, constant speed does not necessarily mean that the acceleration is zero, it's constant velocity that means that our acceleration has to be zero. All right, let's do one last practice problem here today. So we see that if the clock hand velocity at the 12 is 0.7 centimeters per minute in the x-hat direction, and then when the clock hand reaches the 3, its velocity is now minus 0.7 centimeters per minute in the y direction, we want to know what is the average acceleration over that time frame when the clock is moving from the 12 position to the 3. Okay, so to answer this question, we just have to remember that the average acceleration is change in velocity over change in time, and then we have to think about what's our initial velocity and what's our final velocity here. So our initial velocity is the velocity when the clock's hand is at the 12, which we're told is 0.7 centimeters per minute in the x-hat direction. So you'll notice here that this term in parentheses, that's like our Vx initial. Vy initial is actually going to be 0 here. So there's no initial velocity component in the y direction. It's not moving down at all. It's just moving in the x direction when it's right at that 12 position. Okay, so if we want to write out Vy initial is actually going to be equal to 0 here. All right, now let's think about our final velocity. So our final velocity, we're told, is minus 0.7 centimeters per minute in the y-hat direction. So we have something similar happening here. This term in parentheses, it's out in front of the y-hat. So this is going to be V final y, right? That's the y component of V final. If we wanted to think about the x component of our final velocity, that's going to be 0. This hand, it's not moving in the x direction at all at that moment in time. It's only moving down. So we would say that V final x is actually going to be equal to 0. All right, so now we're ready to think about our change in velocity over change in time, which is our average acceleration. We can just take our final minus our initial velocity in the x direction. So that's going to be 0 minus 0.7 centimeters per minute. And then we'll also want to think about our final minus our initial velocity in the y direction, which is going to be minus 0.7 centimeters per minute minus 0. All right, and then we divide by the amount of time it takes for the hand to move from the 12 to the 3, which is 15 minutes. All right, we can distribute that 15 minutes to both the x and y components, and so you should end up with answer B here, minus 0.05 centimeters per minute squared in the x-hat direction and minus 0.05 centimeters per minute squared in the y direction. Okay, so just to kind of wrap up and summarize for today, and also to kind of wrap up chapter 3 here, we're going to be applying our vector rules that we've talked about, so things like splitting vectors up into x and y components, adding and subtracting vectors, and multiplying vectors by scalars. We're going to be applying those principles to two-dimensional kinematics. And we talk about two-dimensional kinematics, we're going to be interested in position, displacement, velocity, and acceleration. Those are all vectors which now can stretch in 2 dimensions, which means that they can each have x and y components, which we can find using trigonometry. All right, so we'll be talking a lot more about two-dimensional kinematics next time. I will see you guys in class.